All right. Good afternoon, everyone. Thank you for coming here today at the CE119 Undergraduate Research Project Midterm Presentation of the Geotechnical Engineering Group. Okay, thank you for attending. We have today the presenters, our undergraduates who will be presenting today. We also have the faculty, advisors, and we also have some MSc students right now. So thank you for coming today. Okay, this afternoon we'll be hearing from 6 undergraduate students who will be presenting uh, the progress of the researches. And yeah, these are some house rules lang. Uh, for the presenters, you'll be given 7 minutes for your presentation. I think ano naman yan, not a problem since you're asked to record a video presentation, right? And then 3 minutes will be allotted for question and answer. And if you can, please open your cameras during your presentation and while you're answering the questions. For faculty and guests, you're invited to ask our students some questions. And if you do want to ask the question live, kindly use the raise hand feature in Zoom so I could recognize and call your name. And alternatively, if you don't want to ask live, you may just ask the question using our chat box. All right. So that's basically our house rules. Now to start off, may I call Leon Dyke Ifuro to present his research on the failure mechanism and behavior of two-tiered bamboo reinforced mechanically stabilized earth retaining wall subjected to isolated footing load. He is advised by Assistant Professor Giancarlo Ventura and the engineer Travis Alcantara. Okay, Dyke?
Hi, good afternoon. Let me share my screen po. Is my screen seen na, sir?
Yes, your screen can be seen.
I'll play the video now.
Good afternoon. I am Leondyke Dre Alifurong, and the title of my study is The Failure Mechanism and Behavior of Two-Tiered Bamboo-Reinforced Mechanically Stabilized Earth-Retaining Wall Subjected to Isolated Footing Load. My advisors are Assistant Professor Ventura and Engineer Alcantara. The general objective of my study is to numerically analyze the behavior, bearing capacity, and associated failure mechanisms of a two-tiered bamboo-reinforced MSE wall under a footing load. I aim to develop a 2D model to estimate critical bearing capacities and failure mechanisms and analyze the effects of different footing widths and locations and upper tier setback distance. Lastly, I will compare my findings with existing two-tier design guidelines and determine the viability of bamboo reinforcements by obtaining their pull-out resistance. My methodology is composed of 3 major parts, which are the data collection, model development and verification, and the results. For the models that I plan to develop for my study, the varied parameters of the wall will only be the footing location, footing width, and offset distance. All other parameters will be kept constant. Different test cases are produced due to the variation of offset distance, footing width, and footing location. My verification model is based on a study of Damians et al. 2013, entitled Comparison of Finite Element and Finite Difference Modeling Results with Measured Performance of a Reinforced Soil Wall. It modeled the soil using Moore-Column, and it is about the predicted response of a reinforced soil wall during construction and surcharge loading. It then compared the results on Plaxis and FLAC, which uses FEM and FDM respectively. Shown on the left is the model from the study, and on the right is the model I created using RS2. It is a 3.6 by 5.95 meter wall and constructed in 32 stages, 24 stages of which were for wall construction with a compaction load of 16 kilonewtons per meter. 8 stages of surcharge application was done with an increasing load of 10 kilonewtons per meter. The mesh I used was a graded 6-noded triangle mesh. The soil backfill is composed of high-quality medium sand with narrow size distribution. Its facing is made of solid masonry concrete blocks angled at 8 degrees while the reinforcements are made of welded wire mesh spaced at 0.6 meters. It has a rigid foundation and the base of the face restricted vertically. The foot of the face is restricted horizontally with a rigid spring with a stiffness of 4 mn per m per m. The facing displacement and reinforcement load will be the results compared from the original study. Results of Plaxis will be the one compared from the obtained data since both Plaxis and RS2 use FEM. The horizontal displacement contour plot at 80 kPa surcharge loading is presented. It can be observed that higher displacements occur at the middle of the wall and lessens towards the top and bottom of the wall. Shown in Figure 5 is the post-construction facing displacement with a datum taken from the end of construction. The coordinates and results were obtained using WebPlot Digitizer to better compare and plot the results of my verification model against the results of the original study. From the graph, it can be observed that the magnitude and trend of my results compared to Plaxis are pretty similar. A simplified model is shown here to better visualize the comparison of my study with Plaxis. The reinforcement loads of layers 2, 4, and 6 were taken during the end of construction and during the application of 80 kPa surcharge. Figure 8 shows the reinforcement load during construction, while Figure 9 shows the reinforcement load during 80 kPa surcharge. For the following figures during the end of construction, it can be seen that the magnitude of values and turns of the graphs from my verification model are similar with the Plaxis results. Same goes for the graphs during 80 kPa surcharge. A dilation angle was given for the soil block interface, but a dilation angle cannot be inputted as an interface property in RS2. Plaxis had a total of 2009 6-noded triangular elements, while RS2 had 1334. A mesh updating option was also used for Plaxis, while RS2 automatically applies the mesh before simulation. My reinforcements were modeled as elastic since it fails to converge if plastic is used. The study originally modeled the reinforcements as plastic. Facing block properties were not explicitly given, therefore I had to obtain it from another study, which used a similar model but with modifications. The graphs earlier for reinforcement load is missing the first point since in RS2, it is unable to obtain the connection load of the reinforcement and block facing. Curves in the graphs of the reinforcement load are not apparent since in RS2, you cannot select the points in the liner where the data will be obtained. They will be automatically selected. The number of points observed is dependent on the meshing and discretization of the model. Also, specific points in the liner that the study observed to make their graphs were not apparent, unlike the graph in the facing displacement, making it difficult to compare and plot the same points. For my parametric study, I obtained my soil and interface properties from a study of Wang et al. 2009. The properties of my bamboo reinforcements were obtained from a study of Salzer et al. 2016, which obtained the properties of Bambusa bomleana, a species of bamboo that is most abundant in the Philippines. My base model is a 6-meter high MSE wall with each tier measuring 3 meters. The reinforcements are 4.2 meters long, spaced at 0.3 meters each. The upper tier offset is also set at 1.2 meters. It was constructed at 21 stages, 20 of which were for construction with an 80 kPa compaction load, while the last stage was the footing surcharge load application. It has a rigid foundation and the base of the face is vertically restricted. The foot of the face has a very rigid spring with a stiffness of 4 mm per m per m. The application of load is displacement controlled with a set displacement of 25 mm for the footing. This displacement was chosen since Terzaghi mentioned that settlements of shallow footings, such as the one I use in my model, are limited to 25 mm only. The maximum shear strain contour plot was plotted to determine the failure surfaces, since according to the Rock Science Manual, maximum shear strain gives a good indication where slip is occurring. For my simulations with the variation of footing location, it can be observed that failure surfaces tend to go towards the facing as the footing is closer to the face of the wall. Higher values of maximum shear strains are confined within the unreinforced soil when the footing is not located within the reinforced soil. Lastly, lower maximum shear strains are experienced within the reinforced soil. The facing displacements with variation of footing location shows that a footing located 0 meters from the facing has the least displacement on the lower tier, but greatest displacement in the upper tier. Increase in footing location shows an increase in footing displacements for the footings located in the reinforced soil, besides the footing 0 meters from the facing. For my simulations with the variation of footing width, it can be observed that higher maximum shear strains occur at higher reinforcement location, and maximum shear strain contours develop at the edge of reinforcements for wider footing widths. The facing displacements with variation of footing width shows an increase in footing width leads to an increase in facing displacement in the lower tier. However, for the upper tier, footing widths of 0.5 meters and 1.5 meters have the same trend and lower displacements, while 1.0 meters and 2.5 meters have the same trend and higher displacement. Thus, more footing widths must be simulated to observe where the change in trend occurs. Shown here is my Gantt chart, and we are in the first week of April. I am on time and still currently modeling different trials and running simulations. These are my references. That concludes my presentation. Thank you for listening.
That concludes my presentation, sir. Thank you for listening.
Thank you. Thank you for that presentation. Do we have any question from our guests? Hmm. Right, can you go to page 26 of your
Yes, sir.
presentation?
Can I just share the PowerPoint file now instead, sir?
Yeah, yes.
Is the PowerPoint seen, sir?
Not yet. Oh, yeah.
Okay. Page 26.
The sources of discrepancies.
Here, sir.
Okay, for the elastic versus plastic reinforcements, you said that you modeled the reinforcement as elastic since the model fails to converge when it is set as plastic, no?
Yes, sir.
Pero dun sa study, plastic yung pagkakamodel dun sa reinforcement.
Yes, sir.
Mm, wh- what do you think? I mean, may ginawa ka ba, for example, to adjustments na ginawa dun sa model kapag plastic yung reinforcement? Di ba, nag-fail to converge siya when plastic. So, baka may other parameters or other adjustments ka dapat na ginawa?
Yes, sir.
Something.
Since in the geosynthetic liner, you're allowed to put the tensile modulus and the peak tensile strength. If you set it as plastic, you have to input a peak tensile strength. However, when I ran my simulations, the reinforcements tend to yield, and because of the yielding of the reinforcement, the model fails, and therefore the non-convergence. So I tried to make it converge by setting it to elastic instead, and with that, the liners didn't fail na, and it continued to converge.
Okay lang na magkaiba, plastic and then plastic.
I tried, sir, with other tensile modulus. I tried because there was another paper with a similar model. I tried using elastic and plastic. It converged naman for both, but with a different tensile modulus since it is a uh different liner. I noticed there was a slight change lang in the facing displacement, but it was very negligible. It was like mga 0.0001 to 0.003
Okay.
meters. So there wasn't really a big change in the results, sir, even for the actual load in the reinforcements.
Okay, thank you. Do we have any other questions from our guests? Case, mukhang wala naman na. So thank you very much, Like, for this presentation. Good job.
Thank you, sir.
Now let's move to a related study from Zachary Villacruz. The study is the mechanical behavior of two-tiered bamboo reinforced metallized earth retaining wall under dynamic load action of vehicles naman. Also by Assistant Professor Giancarlo Ventura and Engineer Travis Alcantara. Okay, Zach?
Yes. Thank you, sir. I'll be sharing my presentation now. Yes, kita po ba? Kita po, sir. Yes, okay. I will begin now. Good afternoon, everyone. I'm Zachary Villacruz, and I would like to share with you my midterm presentation for CE 199. The title of my study is The Mechanical Behavior of Two-Tiered Bamboo Reinforced Mechanically Stabilized Earth-Retaining Wall Under the Dynamic Load Action of Vehicles. My advisors for this research are Assistant Professor Giancarlo Ventura and Engineer Matthew Travis Alcantara. This presentation will cover the following parts. The general objective of this research is to use FEM in observing the mechanical behavior while varying influencing factors of a two-tiered bamboo reinforced MSE wall subjected to dynamic vehicle loading. Specifically, the objectives include, first, to create an acceptable 3D model, second, to observe the mechanical effects while varying loads and wall geometry, and last, to determine the acceptability of the wall based on standards from the FHWA and the AASHTO. To review, this study's methodology is grouped into three main parts. The data collection process, which aims to find the appropriate material properties, wall geometry, and vehicle load approximation methods suitable for the application of this study. The finite element model development, which is done in RS3 by Rock Science, where I will be developing my model and adjusting different variables affecting the structure. This will be done after sufficient validation models of relevant literature. This is where my progress currently sits at this time. Lastly, the results of the simulation will include the structure's response to the loading, namely the backfill stresses, pull-out resistance, backfill displacement, and the failure planes of the soil. The first of my validation models is a simulation of a triaxial test undergoing strain-driven compaction loading. The design of the model is based on a verification study on a true triaxial test provided by Rock Science. I then adjusted the soil properties, constitutive model, and loading to those specified by Manzari and Defalias for compression load, and later on, Defalias and Taibat for cyclic loading. This model features a unit tube with three sides restrained and the confining pressures applied to the other three sides. The varying load or displacement was applied on the top face and in multiple stages. The model was meshed using a four-noded tetrahedra with about 100 elements. Shown on this slide are the superimposed stress strain graphs. The Falias and Manzari tested their model using three samples with varying initial void ratios. A 500 kilopascal confining pressure was applied, and the sample was allowed to experience an axial strain up to 25%. As seen here, the RS3 results agree in value and in trend with that of Manzari and the Falias on all void. Differences can be attributed to the use of FEM for this study. Part 2 of the soil validation includes testing the hysteretic behavior of the soil. From all my testing, I was able to capture different trends from different test cases, which are the stress shear strain response, stress volumetric strain response under constant amplitude, and the stress volumetric strain response under varying amplitudes. Trends were captured by varying the initial void ratios of the samples, a method also used by Tafalias and Taibat. It is important to note that the actual axial strain loadings were not available from literature, so I tried my best to load the sample such that I can clearly capture the trends and yield a similar shear strain value from literature. Apart from this, some deviation is also caused by the idealization of the triaxial test setup into a true triaxial model. Seen on this slide are two varying amplitude cyclic tests on two different void ratios. These tests are strain-driven and show similar trends as in literature. Higher void ratios produce a more spaced out stress strain curve. The peaks extend farther while the opposite is true for the troughs of the graph, when compared to the experimental results in the orange dashed lines. A study conducted by Rahimi 2014 confirms these deviations as their model shows that numerical solutions show that when the stress ratio is negative, the graph is more condensed, while when the stress ratio is positive, the graph is more spaced out. The next test was a stress-driven test with constant amplitude, tested as three different void ratios. Graphed here is the volumetric strain against a deviatoric stress ratio. Higher void ratios produce a more horizontal curve, while lower void ratios have more overlapping between loops and occur at much more of an incline. The last test, showing another stress-driven test, this time with varying amplitude, the trend is also more apparent. The graph on the left from a sample with a higher void ratio only experiences one overlap, while the one on the right constantly overlaps. These responses and trends agree with the results of Pradhan et al., showing that there is only one overlap for the higher void ratio while the lower one experiences multiple overlaps and the graph is also more condensed. My last validation is for the GeoGrid reinforced MSE retaining wall from a study conducted by Huang, Butlers, and Hatami. Shown on the left is their study's model, and on the right is my model made in RS3. This model simulates a stage construction where a compaction after each layer is applied and a gradually increasing surcharge after construction. The soil backfill is modeled with a more column model and reinforced with geosynthetic reinforcements with a wall facing made from concrete panels. This model was meshed with four-noded tetrahedral elements amounting to 23,810 elements. Shown here is the strain distribution at the middle cross-section of the wall. The backfill experiences less strain at the reinforced areas. This shows the displacement on just the geosynthetic reinforcements. It can be seen that the maximum displacements occur at the upper reinforcements and the larger values closer to the edge. Superimposed on this graph are the experimental results from Huang et al. Study and my model at increments of 20 kilopascal surcharge. We can observe that while they share the same trend, the values still do not match. The correction factor was applied to better visualize the trends. A study from Damians et al. Notes that the finite element method underestimates the displacement values when compared to experimental data. I'm still working on improving this model by adjusting different parameters and perhaps compare my results to Damian et al. Study which actually used FEM. After sufficient validation, I'll be able to push through with my parametric study. My test cases include 11 models where the parameters are individually varied. These variables include the tier offset distance, vehicle speed, soil properties, and lane distribution. Looking at my initially proposed Gantt chart, I'm currently behind on my validation models, which I will continue working with hopes to catch up and proceed to numerical testing as soon as possible. That ends my presentation for today. Thank you for listening.
Ayan, thank you po.
Okay, thank you very much, Zach. Uh, do we have any questions for Zach? So for your current progress, behind ka since may kailangan ka pang gawing adjustments for the
Yes, sir, meron pa.
verification sa validation model mo, no, for dun sa yung third,
Yes, sir.
no? So wala naman akong comment for that. I think after mong tawag dito, ma-adjust yung mga required or yung mga pwedeng ma-adjust na parameters, you can just continue sa dun sa
Yes, sir.
tests, right?
Yes, sir.
Wala naman akong questions dun. Other questions po? Mukhang wala. Okay. So, for that presentation.
Okay, thank you, sir.
Thank you. Maybe we can continue to the study of Rendell Para on the effect of groundwater seepage on behavior of soil nailed wall on expansive clay using finite element method. Advised by Assistant Professor Jaime Angelo Victor. Hey, Rendell.
Kita na po ba yung presentation?
Yeah, you can see now.
Okay.
Pero parang mahina yung audio.
Oh. I think naka-max na po siya.
Try na.
Hindi po ba naririnig or mahina?
Mahina lang kanina eh. Try ulit natin.
If ganun po, okay lang po ba i-export ko ulit yung video pero matatagalan siya? I-adjust ko lang po yung volume.
Parang hindi lang po ata nasama yung share sound sa pag-share ng screen.
Okay.
May
So,
checkbox po yun sa lower left.
Okay, wait. Okay. Good afternoon, everyone. Narinig na po ba yan?
Yeah.
Okay, thank you.
Clear na.
Good afternoon, everyone. I am Rendell Para, and I will be presenting my thesis entitled Effect of Groundwater Seepage on the Behavior of Soil-Nailed Wall on Expansive Clay Using Finite Element Method. The presentation will contain the following: an overview, the objectives, the methodological framework, progress report, and last is the concert. Among the different soil stabilization techniques, the application of soil nails is one of the technically efficient and cost-effective method on stabilizing slopes, excavations, and retaining walls. Its behavior highly depends on the type of soil where it is installed. The stability of soil nails on expansive clay is significantly affected by the shrinking and swelling behavior of the soil when subjected to moisture. To understand its behavior, finite element analysis is the recommended process to avoid the limitations provided by other methods. With this in mind, this research is done to achieve the following objectives. First is to perform a 2D finite element analysis using the RS2 software involving soil-nailed walls on expansive clay. Second is to investigate the effect of groundwater seepage on the displacement and stresses of the soil and the structure. And last is to determine the failure conditions by varying the independent variable, in this case, the groundwater seepage. To achieve those objectives, the procedure shown in this methodological framework will be followed. First is the data collection. These are the preliminary data that are needed to model the soil and the structure. This includes the properties and dimensions of the soil, the structural interface, and the soil nails. Since these data are not easily obtained, most of it are adapted from different researches. Next is the verification that involves verifying if the properties used will accurately model an expansive soil. After the model is verified, the actual modeling will be done by defining first the soil profile that involves the geometry, the mesh, and the boundary. Once those are defined, the properties of an expansive soil that are adopted from other researches will be imported. Stages are then made to show the progressive installation of the wall and support. I created 14 stages showing first the installation of the structural interface, then alternating excavation and installation of soil nails for every 2 meters, and once the wall and the support is installed, an overburden is added to take into account the natural load existing in an area. And lastly is the addition of ponded water resulting into a seepage of water underground. Different test simulations will be done by varying the seepage of the groundwater, where stresses and displacement of the soil and the support will be analyzed. And last will be the determination of the failure conditions of the support and the wall. And now, here is my current progress. I already have the result of the verification model. The model is a simple 10 meters by 10 meters soil that is subjected into a 15 meters head steady state groundwater seepage without any overburden. This is the initial state of the soil where no significant displacement is observed, and upon the addition of groundwater, here are the results. These are stages of the result of the soil displacement. The last figure shows the deformation vectors of the soil. Based on this result, the expansion occurs on the whole model with the maximum vertical displacement of 1.6 cm. However, these are just initial interpretations that needs further consultation. Then after validation, the actual model will be done before the analysis. For modeling the actual project, the same properties from the verification model are used, and here are those soil properties and the references where those values are adopted. Just like what have been mentioned earlier, these values are hard to obtain in this setup which needs laboratory tests. For the geometry of the soil, here are the dimensions with a length of 40 meters and the height of 18 meters before excavation. And each excavation has a depth of 2 meters with a total of 10 meters and an excavated length of 10 meters. And here are the stages mentioned earlier with the following description, and here are the mesh and restraints used for the project. Unlike previously, a greater number of nodes is used to take into account the smaller elements. Then the bolt and the wall are also modeled, but since modeling the structure element is not the focus of this study, these are properties from RS2 default settings. And that is all for the progress. And here's the Gantt chart. This chart is updated with the addition of verification part, unlike the previous RPM. The verification is expected to be finished at the end of March so that test simulations can be started this April. And for this reading breaks, simulations, data gathering, and analysis is expected to be done. And here are my references, and that is all. Thank you.
Yeah, thank you. Thank you very much, Rendell. Welcome na yung mga questions for this presentation. And may tanong po ba? Doc Z? Yes po.
Okay, so I'll follow up my question. The last time I recall you presented, how are you taking into consideration the swelling? My question there is that, so when the soil swells, how do you correlate the water content with the swelling pressure? That's my first thing. Then how are you going to correlate the shear strength with the water content? Because theoretically, soil swells, the water content increases dramatically. So the shear strength will decrease. And in your camp claim model, the M there is not, the M I think is only for a particular water content.
Hello sir, so mag-start po muna ako dun sa verification model. So, ang ginawa ko po dito sir, just like what have been uh, advised last RPM, in-expose ko po siya in a groundwater in steady state, and here are the results. So, I'm expecting na I will base the expansion of the soil based on the vertical displacement of each element, and yun sir, yun yung
Okay,
maging
pero this is, you said this is steady seepage.
yes sir, steady
Okay,
state.
but then how do you know that the vertical displacement is not due to the seepage forces? Because the seepage creates its own forces. Diba? Whether or not the soil is expansive, there are seepage forces. So how do you know it's not due to that and really due to the expansion of the soil?
I think sir, maybe I can create another verification model using static water instead of steady state.
Okay, and then see.
Yes sir, based on the
So,
vertical
but then, okay, so if you put it there, where's the parameter in the model that, and then, okay, so, but the static is if you add water, then it could also be because of the change in effective stress, that's what's going to cause the vertical displacement. So even that, I don't think will be due to the swelling of the soil, because it's one thing for a change. In other words, if the soil is not expansive, uh, the decrease in effective stress will still happen and the vertical displacement will still change. So even a static value, even though it's static, doesn't mean that it is due to the swelling. I presume that that is what you want to model here, because you said this is expansive clay, so a swelling, so that has to figure out somewhere in the model. And camp clay, if you're saying that there's a swell, that's the other term for that is rebound. That's done when you unload. The sample will swell. So that's why they call it a swell index. But it's not related to the change in water content. And then as the water content changes, then the undrained shear strength should go up, because the void ratio will go up. So maybe that is what you need to look into, if that's my comment. Okay.
Okay sir, I'll look into that.
Thank you, Doc Z, for that question. May other questions pa po ba kayo for Randel? Okay. Wala na. Since wala na, thank you very much for that presentation. Okay, we can now move to Mariel. Okay, Mariel Gwen G. Martinez will be presenting her research on the assessment of remotely sensed antecedent soil moisture measurements for the development of a framework for landslide early warning, a case study in Benguet, also advised by Assistant Professor Jaime Angelo Victor. Okay, Mariel?
Kita na po ba yung presentation?
Yes, the presentation can be seen now.
Okay, I'll be starting the video now.
Good day. I am Mariel Martinez, and my topic is the assessment of remotely sensed antecedent soil moisture measurements for the development of a framework for landslide early warning, a case study in Benguet. My advisor is Assistant Professor Jaime Angelo Victor. Landslide is a geological hazard that is generally characterized by the downslope movement of a mass of rock, debris, or earth under the influence of gravity. Morphological and non-morphological factors affect slope stability, and external stimuli can trigger landslides. In tropical regions and mountainous areas, a high proportion of landslides are triggered by rainfall. Early warning systems help with the mitigation of harm or loss through the delivery of timely information prior to a catastrophic event. The provision of empirical rainfall thresholds is a simple and affordable approach for landslide prediction that uses historical information to establish a link between rainfall conditions and the occurrence of landslides. Empirical rainfall thresholds have been linked with the generation of multiple false alarms. One possible reason for this is that variations of critical hydrological properties in the ground are represented by rainfall characteristics as proxies. Weak relationships have been found between antecedent precipitation and real soil moisture variations. Additionally, obtaining in situ soil moisture data for landslide prediction is often difficult due to the lack of available soil sensor networks. For objectives, the general objective of this study is to assess the potential of remotely sensed antecedent soil moisture measurements for landslide early warning by comparing conventional empirical rainfall thresholds with thresholds derived by integrating antecedent soil moisture information using a case study of the province of Benguet. The specific objectives are to develop thresholds that consider the effect of soil moisture using a probabilistic approach, to investigate the influence of environmental features on RS thresholds, to investigate the influence of antecedent soil moisture measurements on the triggering rainfall parameters, and to quantitatively compare ED thresholds and RS thresholds. For the significance of the study, the increasing risk for the occurrence of rainfall-induced landslides in the Philippines necessitates reliable and affordable measures for landslide mitigation. There is still a significant gap between the abundance of remote sensing soil moisture products and landslide studies utilizing such data, and the integration of soil moisture to rainfall thresholds has been tested mainly in Mediterranean, temperate, and alpine climatic settings. For scope and limitations, the study is limited to rainfall-induced shallow landslides. Rainfall data was derived from 24 rain gauges from the OST, ASTI, and PAG-ASA. Environmental features to be considered in the study are limited to slope, land cover, and soil texture. Soil moisture information was obtained from the NASA SMAP Level 4 Global 3 RLE 9 km East Grid Surface and Root Zone Soil Moisture, Geophysical Data version 6. Historical landslide records were obtained from NDRMC situational reports and news reports, and the analysis period is from March 31, 2015 to December 31, 2021. Here is my conceptual framework. For the study, the thresholds to be assessed are the ED and RS thresholds using the empirical and probabilistic methods. Also shown are the considerations for this study. The two articles shown serve as the main reference for the methodology, with Abraham et al. Study as the basis for the development and comparison of RS and ED thresholds, and Zhu et al. Study for the discrimination of RS thresholds by environmental features. Shown in this slide are additional references. The 2021 study by Zhao et al. Serves as the reference for choosing the remotely sensed soil moisture product used for the study. For the methodology, first the collected data and limiting parameters were processed into the calculation of rainfall-induced landslide thresholds tool, or CTRLT. A CTRLT uses an algorithm-based approach which automatically reconstructs rainfall events and identifies rainfall conditions that have triggered landslide events from which the thresholds are derived. The AD thresholds produced by the algorithm are in the form of a power law. Since traditional empirical thresholds are limited to producing a single output, which contributes to a larger chance for false alarms, this study considers the probabilistic determination of thresholds using the two-dimensional Bayesian approach. Once probabilistic thresholds are defined, the RS thresholds will be discriminated according to land cover, slope, and soil type. Finally, the quantitative comparison of the performance of the thresholds will be carried out through the receiver operating characteristic approach, from which the best model will be identified. For the empirical thresholds, 126 out of 143 landslides and 5,128 rainfall events were considered by the CTRLT algorithm. 17 landslides were discarded by the algorithm due to the missing data from rain gauges and in compliance of the rainfall events with limiting parameters. Note that although 126 landslide events were used by the algorithm for the definition of empirical thresholds, only 63 rainfall events were identified as triggering because some of the rainfall events were identified to cause multiple landslides. The threshold lines, which correspond to different exceedance probabilities, were used to classify the rainfall events into different categories. It can be observed from Table 1 that the relative uncertainty of both the intercept and slope exceed the reliable relative uncertainty value of 10% for all threshold categories. The rainfall events reconstructed by the algorithm were then used for the probability distribution of E and D. For the first case, only 5,115 out of 5,128 rainfall events were considered, as outliers were ruled out. For For case 1, L is defined as the occurrence of at least one landslide for a given rainfall event. Therefore, without the outliers, only 59 triggering rainfall events were considered. It can be observed that two conditions have a posterior probability of 1. This is because all of the rainfall events identified with such conditions resulted in two landslides. This may require me to revise the intervals within the ED plane to obtain a better distribution of the landslides. Moreover, there are several cells within the matrix which have no landslides. This may be attributed to the limited inventory of landslides used for the study, rather than the absence of landslides. For most combinations of E and D, in general, it can be observed that at larger measurements of event rainfall, the posterior probabilities of landslide occurrence are higher. The approach used for case 1 neglects the number of landslides triggered by a given rainfall event. Therefore, another approach would be to replicate such rainfall events based on the number of multiple landslides. Therefore, for case 2, 5,175 rainfall events were considered, with 118 triggering rainfall events. Similar with case 1, case 2 generally demonstrates that at higher event rainfall measurements, posterior probabilities of landslide occurrence increase. As with case 1, it may be useful to revise the intervals in the ED plane to obtain a better distribution of the posterior probabilities. For the consideration of antecedent soil moisture, the daily average root zone soil moisture measurements from NASA SMAP were used. The root zone soil moisture measurements in Benguet ranged from 0.5 to 1 for the study period, which served as the basis for the categories for the probabilistic distribution of R and S. The maximum probability of 0.268 can be observed at the most extreme event. Moreover, the probability distribution demonstrates that even less severe rainfall events can result to landslides at more moist soil conditions. The same trend can be observed with case 2 for the probability distribution of R and S. However, it can be observed that the posterior probability values are higher for case 2 than case 1, particularly for the more extreme events. Here is my work schedule, and here are my references. And that concludes my presentation. Thank you for listening.
Thank you, Marielle. We have questions for Marielle about her research and progress. Marielle, you have, I don't know, you have any yung initial results mo na yun. Yung number 1 is consideration of the of the rainfall events, tama? Tapos yung
Yes.
pangalawa is consideration of the antecedent soil moisture.
Yes po.
Anong next na part ng study mo?
After po nito, I will be defining critical probabilities based on the distribution based on this probability distribution figure. And then I will determine the corresponding threshold categories for each range of soil moisture. Tapos same goes with the probability distribution of E and D also. I will determine the critical probabilities and then determine the corresponding duration to the event rainfall, vice versa. So from there, I will be using the receiver operating characteristic curve to compare the results of the two by plotting the specificity and the sensitivity and specificity. And from there, I will compare the area under curve. So whichever has the greater area under curve, that will be considered as the best model for landslide prediction.
Thank you. May questions pa po ba? Sir Travis?
Siguro hi Mariel, related dun sa tanong ni Heli. Hindi ko pa kasi na-imagine yung ultimate output.
Yes, sir.
So yung ano yung magiging ano yung pinaka-expected output ng research?
Basically, sir, the final output would be to compare the empirical threshold without considering the antecedent soil moisture and with considering the antecedent soil moisture. So that will be done using this receiver operating characteristic approach.
So, parang, ano yun? Threshold yung hahanapin, di ba?
Yes, sir.
Threshold ng rainfall with and without the antecedent moisture.
Yes, sir.
Okay, okay. Sige. Tapos, specific lang yun doon sa buong Benguet. And,
Yes.
naka, nakadepende doon sa soil kung saan natin siya in-observe, correct?
Sorry, sir.
Yung, kasi you said earlier, you discriminate it with, ano yun?
Oh, yes, sir.
Okay, okay. Sige. So, ito, medyo madami pang process after this kasi marami ka pang titingnan. Tama, di ba?
After this po, yes po, yung for the discrimination of the thresholds po.
Okay.
Pero that part actually po won't be used for the receiver operating characteristic approach. So that will only be used for parang qualitative ano lang po, assessment lang po. Just to determine the effects of slope, land cover, and soil type on the antecedent soil moisture parameters.
I see, I see. Okay, sige, sige. Thank you, Mariel.
Thank you po.
Thank you, Sir Travis. May other questions pa po? Okay, since wala na, thank you very much for that presentation, Mariel.
Thank you po.
And now, we can now call Nisa. Okay, for Nisa Cartin, her study is on the rate of bacteria-induced strength deterioration of abaca fiber geotextile. Her advisor is Assistant Professor Lestel Torio Caimo. Okay, Nisa?
Okay, sir. I'll be sharing my screen na po. Kita na po ba?
Yes, kita
Okay,
na.
so I will be playing it na rin.
Good day, everyone. I will be presenting my current research on the rate of bacteria-induced strength deterioration of abaca fiber geotextile with the guidance of my advisor, Ma'am Torio Caimo. Here is an overview of my presentation. So let us first discuss geotextiles, which are materials used in engineering that has separation, reinforcement, and erosion protection mechanisms, among others. There are two general types of geotextiles, natural and synthetic. In the industry, synthetic is more commonly used. However, when synthetic geotextile deteriorates, it leads to the accumulation of microplastics. Furthermore, microplastics may alter soil properties, such as decrease in soil bulk densities and the weakening of forces holding the soil particles together. The conscious consideration of the environmental impacts of synthetic geotextiles has trailblazed the emergence of studies on natural fibers as possible alternatives. Now, abaca fiber is native to the Philippines. The fiber is known to have excellent tensile strength owing it to its cell wall composition. The abaca industry has also provided the Philippines positive benefits over the years, and it may be reflected with the annual average earnings from exportation alone, which has reached 4.7 billion pesos. Given these, abaca may serve as a potential natural geotextile-based material. However, one of the disadvantages of natural fibers is its susceptibility to physical, mechanical, and biochemical deteriorations. The aforementioned factors will be addressed in the research, specifically the effects of bacteria and the rate of the natural fiber's strength deterioration. The objectives of the study include simulating the in situ condition of soil by inducing bacteria in the soil reinforced with abaca fiber, determining the rate of the material's mechanical deterioration through tensile strength test, testing the suitability of treated and untreated abaca fiber as a natural geotextile by measuring its grab tensile strength, and identifying the reinforcement capabilities of abaca fiber geotextile by conducting a CBR test in the soil of application. Exploring a natural alternative whose base material is readily available in the country may be beneficial both in an environmental and economical context. Assessing the abaca fiber's geotextile capabilities as well as considering its limitations will aid in understanding the extent of its reinforcement mechanism. The study will utilize abaca fibers with a normal grade, and its rate of deterioration and reinforcement capabilities will be tested. However, the study will have the following limitations: the type of soil of application, the type of bacteria to be induced, and the method of fiber weaving. The tests will also be limited to checking the tensile strength of the fibers using ASTM D4632, while the soil CBR test will be based on ASTM D1883. Abaca fiber geotextile as a soil reinforcement technology is the focus of the study. Specifically, the abaca fiber's properties and strength deterioration as it is subjected to natural forces in the soil, such as microorganisms, will be studied to assess its overall tensile strength. Here are some of the literatures I plan to use as guides throughout my research, though there is one study that I would like to emphasize, which is a similar work done by my advisor, wherein they conducted an experiment testing the grab tensile strength of banana fibers after its application in bacteria-induced soil. The paper will serve as one of the main references of my study since I will pattern my methodology in the procedures stipulated by the authors. As an overview, here is my methodology. The experiment will have the following setups. There will be a control setup of the raw soil without any embedded abaca geotextiles, and there will be 3 different test cases. First would be the raw soil with geotextile, and the soil will be oven-dried to eradicate as much as possible the effects of the naturally occurring bacteria. The second case would be soil induced with bacteria and added with geotextile. This is the more realistic setup wherein the natural soil condition is simulated through the addition of a known bacterial solution. Lastly, there will be soil induced with bacteria and embedded with kerosene-treated abaca geotextile. This is to observe whether treatment of geotextile will strengthen and prolong its service life and increase soil reinforcement. The first step in the methodology, which includes the canvassing and procurement of the materials and test prices, were accomplished last January. For the soil preparations, I was able to conduct 3 trials of sieving, and also 3 trials of liquid and plastic limit tests were conducted. The following are the procedures and equipment used throughout the testing proper. The results obtained after the sieve analysis and Atterberg limits test are as follows, and averaging the values from all trials, it can be observed that the soil is lean clay with sand and has medium to high plasticity. On the other hand, the weaving of the abaca fibers was done with the assistance of the Philippine Textile Research Institute or PTRI. Each geotextile has a dimension of 4 by 8 inches and apertures of 6 by 10.5 millimeters. Now, considering both the control and experimental setups, the soil specimens were oven-dried to remove any naturally occurring bacteria present. The soil was then placed in 3 separate plastic containers. The first container was set aside since this contained the control setup. Now the raw soil, to be embedded with abaca geotextile, was placed in the second container. On the other hand, the third container was used to hold the soil induced with bacteria. The inducing of bacteria was done by adding 4 teaspoons of EM1 bacterial solution in a liter of water. Then this mixture was poured onto the soil. Since a bit of clumping occurred, I decided not to pour the entire 1 liter solution in just one go, since this might not lead to equal spreading of bacteria in the soil specimen. So I tried to scoop out some soil, placed it in a bowl, and mixed it thoroughly with 1/4 to half a cup of bacterial solution. This process of scooping and mixing was repeated until the 40-liter plastic container was filled with bacteria-induced soil. We also have here the treatment of the abaca geotextile, which was done by submerging it in kerosene for 2 days. Finally, after all the preparations, the abaca geotextile and kerosene-treated abaca were integrated into the soil. Also, every day, the moisture or the humidity of the soil is checked through the use of a digital hygrometer. After a substantial amount of days, in this case for 30 to 45 days, the geotextiles will be extracted from the setups and will undergo tensile strength and CBR testing, and the following are my prospect dates of testing. This is my work schedule. Now that the integration of geotextile into the soil is done, the next steps would include the continuous observation of the test specimens, the preparation for the CBR and tensile strength test procedures, and the fixing of the current contents of the manuscript. These are my references, and that concludes my presentation. Thank you for listening.
Thank you, Niza. Do we have questions for Niza? All right, Niza, you have 3 setups, right? Number 1 is your control setup. Number 2 is your setup with the bacterial solution. And then number 3 is yung bacterial solution for the soil, and then kerosene treated na geotextile. Question ko lang, ano yung laman ng bacterial solution? I mean, ano lang, background lang
Sir,
about your
sige.
bacterial solution.
So, meron po siyang yeast and molasses. Yun yung components ng bacterial solution na po
Yeast
na
and
yun.
molasses.
Yes po.
And that's the naturally occurring na bacteria then
Yes
sa
po.
soil. Okay? And then for the treatment ng kerosene, ano yung reason why kerosene yung chosen as the treatment for your bacteria?
So, sir, I'll move to my RRL. So, a study by Ramasubarao. So, what he did in his study was he submerged coir fibers in kerosene for a day, 2 days, and 3 days. And he saw that the optimal submersion of coir fibers was for 2 days. So, I also did that with my abaca fiber because submerging it in kerosene for 2 days would lead to the decrease of water absorption content. And we want that because presence of water in the environment would cause the more inducing of bacteria, and the inducing of bacteria would lead to consequently and theoretically the attacking of the tensile strength and the other properties of the fibers, like its cell wall basically.
Thank you. Clear naman na. Do we have any other questions po for Niza? Mukhang wala naman na. So, just continue on your... Ano yung next mong step again?
So continuously checking it and observing it po for any changes in moisture content and also preparations for the CDR and tensile strength testing.
And meron ka naman ng location for the testing, no? So,
yes po.
Waiting na lang talaga. Alright, sige. Very good.
Thank you, sir.
Thank you, Niza. We can now move to our last presenter, Anton Lorenzo Tiope, on his study on the analysis on the viability of polylactic acid thermoplastic as a biaxial geogrid material based on capabilities. His advisor is Assistant Professor Jaime Angelo Victor. Okay, Anton, you can now present.
Kita po ba yung video?
Yes, kita na.
Okay. Play ka na po. Rinig naman po, no? Rinig po ba?
Yung audio, wala. Baka hindi mo rin na-share yung audio like yung kanina.
Opo, ayun. Kita na po, no?
Yeah.
Play ka na po.
Good day, I'm Anton Tiope, and I'm here to present my thesis entitled The Analysis on the Viability of Polylactic Acid Thermoplastic as a Biaxial Geogrid Material Based on its Tensile Strength Capabilities, and my advisor is Assistant Professor Jaime Victor. Geosynthetics are a common material used in geotechnical engineering and is made of synthetic or natural materials that come into contact with the soil or aggregates for the purpose of improving the soil or the soil structure. One kind of geosynthetic are geogrids, which are mainly used for reinforcement purposes and are made through heat welding, extruding, or from punching patterns. Normally made of petroleum-based plastics, however, a new material may prove to be a worthy alternative. These are bioplastics. They are material made of plant or other biological material and share the benefits of plastic, being malleable in shape. They are made from renewable materials and are generally biodegradable. One such material is polylactic acid, which is a bioplastic made from lactic acid obtained from glucose or sucrose. Throughout the recent years, this type of bioplastic has been rising in popularity, and this research aims to study whether they're a good alternative to other petroleum-based plastics for the use as a geogrid material. Stated, most geogrids are made of petroleum-based plastics like polyethylene and polypropylene. This research aims to provide an alternative, polylactic acid, which is a renewable material, making it more sustainable. It also aims to analyze the strength of this material and assess whether it is equally viable to that of the petroleum-based plastics used for geogrids today. Not much research has been done discussing the applications of polylactic acid in engineering, and this research aims to address that by comparing polypropylene and polylactic acid as geogrid materials by directly comparing their properties as geogrids and their reinforcement capabilities when applied to an embankment using the Flax Slope 8.1 program. The general objective of this study is to create a polylactic acid plastic geogrid and determine if it is a viable alternative to those that are commercially available. The specific objectives is to create a geogrid based on the SS40 geogrid model and compare its tensile capabilities to polypropylene, specifically at 2% strain, 5% strain, and its ultimate tensile strength. Additionally, there would be a comparison on the applicability of the grids when applied to an embankment structure. Here is the conceptual framework showing all the aspects related to geogrids and geosynthetics related to research and highlighting the important factors that I would be considering for the study. The related literature include a book entitled 3D Printing with Biomaterials Towards a Sustainable and Circular Economy, which presents the possibility of using polylactic acid for engineering purposes and describes the potential, characteristics, and uses of PLA. Another is a research by Farah, which shows the physical and mechanical properties of PLA along with its functions and would be used to analyze the PLA geogrids after the testing. Next is a study by Wulandari and Tahandra entitled The Determination of Optimal Tensile Strength of Geogrid Reinforced Embankment, which will serve as the base research where the method of comparing the capabilities of the PLA and polypropylene geogrid will come from, along with supplying the needed additional variables to run FLAC. This is the methodological framework where the geogrid models would be created and would be tested in terms of its tensile strength at 2% strain, 5% strain, and ultimate tensile strength. A cost analysis would be done along with a comparison of the PLA and polypropylene geogrid. A comparison of the tensile strength values would be done along with a comparison on the effectiveness and applicability using the FLAC Slope 8.1 program, which would ultimately show if this material would be viable to explore as an alternative. Single rib tests would be utilized to obtain the tensile strength, and this would be done in accordance to the ASTM 6637 standard. Shown is the embankment taken from the research by Wulandari and Tahandra, which was replicated using FLAC version 8.1 instead of FLAC 4, which was used in their research. This yielded a factor of safety of 0.69, which was different from the factor of safety obtained in the research, which was 0.79. A geogrid reinforced embankment was also modeled with a tensile strength of 20 kilonewtons per meter and had a factor of safety of 0.98, which matches up to the research by Wulandari and Tahandra. The properties of the polypropylene SS40 geogrid was also applied in the FLAC analysis, which used a bond strength of 500 to 6,000 newtons per meter and a bond friction angle of 35 degrees, which yielded a factor of safety of 1.025 to 1.053. This SS40 geogrid analysis was done with a bond friction angle of 30 degrees, yielding a factor of safety that ranges from 1.018 to 1.045, lower than the bond friction angle of 35 degrees. Continual lowering of the bond friction angle was done at intervals of 5 degrees until the lowest was achieved, which was 5 degrees bond friction angle. The graph shows the factor of safety in relation to the cohesion and bond friction angle, and it shows that as cohesion and the bond friction angle is decreased, the factor of safety also decreases. Although not reaching a minimum factor of safety of 1.5 as specified by Wulandari and Tahandra's research and a research entitled Ground Improvement Case Histories. This, however, provided substantial improvement as the polypropylene geogrid increased the factor of safety by a value of 0.149 to 0.363. Also seen is a general decrease in the wedge size, meaning a smaller portion of the embankment would be displaced. Next is a cost analysis where the Tensar SS40 polypropylene geogrid is compared to the polylactic acid geogrid. A direct cost analysis was done which compared the market cost of the Tensar SS40 geogrid to the production cost of the SS40 polylactic acid geogrid done in the study. As seen, the SS40 geogrid is significantly higher in terms of cost compared to the polypropylene geogrid, and this is attributed to the material cost and the production method. The Tensar SS40 geogrid was a factory-made product which was done through mass production, which is significantly cheaper than 3D printing. As seen, the cost of PLA production is also significantly higher than that of polypropylene. However, researches are currently being done in order to refine the production method even more to cheapen the price, making it a viable alternative to explore in the future cost-wise. This is my Gantt chart showing the schedule for the research, and testing of the GeoGrid would commence sometime this week or next week. These are my references, and thank you for watching.
Thank you, Anton. The floor is now open for questions about the presentation. Sir Gian, go.
Hello, Anton.
Hello po.
Can you discuss more about the modeling that you did with FLAC? Like, how did you model the geogrid? What are the loading conditions? Para lang clear sa amin kung paano mo ginawa yung model.
The Flax Slope 8.1 program po was a more refined and simplified version of the FLAC program that is mainly used for embankments and slopes. So the embankment that I created was only subjected to gravity loads from the soil, and I based my model off of Wulandari-Tajandra's model. It would be a hold on pa. I will share po the model.
Ako, bumili ka na daw ng Microsoft 365.
Medyo mahal po. Ito po yung model. I replicated their model po as a form of verification din po, and I'd be using their model to simulate the embankment structure, the performance of the geogrid in the embankment structure po. Each of the 5 layers would have a geogrid po, and the main variable that varied sa test of each geogrid was the cohesion and friction angle, since these values po were not part of my study or research na obtainable, and it would be difficult to obtain the cohesion and friction angle values of the geogrid when applied to an embankment structure. The soil...
I'm not that familiar with FLAC, pero meron din ba silang, I mean, when you tried to come up with the model, does it also consider construction sequence? Or minsanan yung pag-load mo sa dulo na lang, or yun nga, yan, parang ganyan, per layer. Gagawin mo na yung sa ilalim ng first layer, and then ilalatag, and then the next part, and so forth and so on? Or is it as one?
The construction method po of the embankment was the whole embankment was created as one po, and then the geogrid would be added afterwards as parang it would be added into the embankment po. Yun. With no specified layer po sa FLAC mismo. But
so dun sa tingin ko yung possible sources of error na hindi siya per stage yung loading mo. So you might want to consider that and look into that as well. Kasi usually kapag ganito, you do it per stage. So construction sequence, parang ganon. So I'm not that sure, pero tignan mo na lang.
Okay po.
Ayan, sabi din ni Ma'am Les. Check mo lang din yung comments. May comments niya yata si Ma'am Lestel and si Doc Z about it. Yun lang naman on my end. Thank you. Thank you, Anton.
Okay po. Kay Sir Zarko po, what do you mean, sir?
The FLAC, I know as the construction, the field placement. Kasi what Gian is referring to is that the embankment construction is simulated with the field placement. However, I know that FLAC slope is specifically made for existing slopes. So baka it does not have the field placement option, because to simplify the program, because I know itong si FLAC slope, Itasca gives that for free as an incentive.
Okay po.
I'm not sure. Bakit? Did you download it?
Actually, the whole FLAC yung program po if I'm not mistaken, was already free po based as of last year.
Oh, okay.
But I chose flax slope po since based on certain tawag doon, I've seen certain classes po on flax and flax slope. Based on that po, based on the classes po, I thought na flax slope would be the most appropriate program since it was able to replicate in terms of the visual and needed output, which was factor of
Okay.
safety of the research of Wulandari and Tahanda. To answer Ma'am Tori's question po, yung flax slope po has a feature of including geosynthetics into the embankment. The geosynthetics isn't really specified. However, I've seen certain researchers then po using flax slope, which assume the geosynthetic to be geogrids. And yung cohesion po and bond friction angle po, since it was not obtained, I chose a range po that included Wulandari and Tahandra's values for cohesion and bond friction angle. There was no option po of specific geogrid types. The only values that I could input po were yung stiffness modulus, tensile strength, which I varied to fit the tensor geogrid, and which I would also vary to fit the geogrid which I have created using polylactic acid, and the cohesion values and bond friction angle. Yung the tensor po was cheaper. In terms of total cost po, for the given product, it was more expensive, but the cost per square meter po was cheaper. However, I also included a possibility that the polylactic acid geogrid could be more competitive in the future, since certain steps in between the production methods in the polylactic acid creation was being researched upon to remove, and would therefore cheapen the price of the polylactic acid as a material.
Thank you, Ma'am Lestel. Thank you, Doc Z. Thank you, Sir Jen. And thank you, Anton, for that presentation.
Thank you po.
Just have to continue this. Okay, thank you. So that actually concludes all the presentations for today. So thank you very much for all the attendees. Our next schedule would be on April 20, 28? 29. Okay, parang 4 weeks from now. Your RPM number 3. So yeah. But before we exit or before we end, siguro mag-picture muna tayo. Naka-share pa rin yung screen mo, Anton. Okay, thank you.
Nasa office pala si Ma'am Lestel.
Sir Travis, paano lang?
Ako na ba? Sige, wait lang. 1, 2, 3, smile. One more po, one more. 1, 2, 3, smile. All right.
Okay, sir. Thank you very much, everyone. Continue lang natin yung progress natin para makaabot na tayo sa final presentation. Final agad. Okay, anyway, thank you very much again, and I hope you have a good weekend.
And reading break.
And reading break.
And Holy
Tama
Week.
pala.
Reading break
Thank you
na.
guys. Thank you, Heli, for moderating.
Thank you, sir.
Bye-bye.
Thank you.
Thank you
po.
po.
Ay, ako pala yung host. Bye-bye.